on the left.
Sorry, Fabrice.
Sorry. On the left, you see there is that's a picture of the actual an actual wafer. Okay. So maybe to make the things clear, people usually refer to PIM, processing in memory, doesn't mean the same things always. It depends on the people you speak with. So you have the, I will say, to make the things more precise, you have the in-array computing, where you will exploit the electrical properties of your bit cells to make some kind of calculation, very simple, on your, that's fundamentally the basis of your calculation. So this has been envisioned, I will say, so far only on non-volatile memory. I'm not aware of anyone which has tried to do so on DRAM. And as I will explain later, I do not recommend to try. So today I will say that all these in-array computing are flash-based, but there are many papers on probably many research projects about using exotic non-volatile memory technologies to pursue in-array computing. Then you have in-die computing. So you have your classical array of memory, and along it you will have an ASIC core in the same process, in the DRAM process, which will handle the calculation, and it's very close to the DRAM array, so you have lower latency, higher bandwidth than you could get otherwise. So we are the pioneer of this approach. Samsung has announced what they call FIM, function is memory, which is a very specialized engine which is not really programmable. We know about a company, Neuroblade, an Israeli company. I have an idea of what they are doing because I have read their patent, but I will say I'm not sure if they have got their chip right now or not. This is not clear. So I don't know if there are 3 or 2 companies with an actual product. Okay. Then you have the stacked die computing. The idea is, okay, since it is very difficult to realize logic on the DRAM process, it is tempting to say, okay, I will have DRAM's dies, and I will have stacked over them or below them, I will have a logic die. I will use a TSV for interconnect, and I will still be close to my data, while I'm having the advantage of using a logic process for all the for implementing the calculation unit. So at the time of HMC, which was hybrid memory cube, which was a Micron technology on Micron product, they had the logic die, very fast SerDes, a few logic, and DRAM stacked over it. And obviously, many people said, okay, there must be area free on this logic chip. We should add calculation, and it will be a great product. But Micron never followed suit on this. And having read their patent about the thermal tricks he tried to use to remove the heat even from the logic die of the HMC, I believe I know why. They had a lot of problem moving away the heat from the logic die, such that everything worked fine. So HMC has been plagued by very high manufacturing cost. In fact, the only product I saw using HMC, you had a board with a big Xilinx FPGA, and you had in two flavors, HMC or GDDR6. And it was the GDR6, it was $10,000, and the HMC was $20,000. And there was only one HMC chip. So I believe you understand the problem. Now you have DIMM level computing, which is okay, we will put an ASIC or FPGA on the DIMM. We will use standard DRAMs, and we will make calculation. We are closer than on the server. Okay. I don't know of any product in this area. There are papers on companies with things to this concept, but nothing concrete so far. And then I will say we have in storage computing, which is typically putting a processor at the beginning of FPGA and ASICs on a big non-volatile memory, on a big flash disk. You have a company named NGD System, but they have a few competitors which are doing exactly the same things than them. Okay, so I will say this is a 5 family you can think of when you think to processing in memory. On which one is, it depends of the context. Okay, so concerning UPMEM, we had 8 32-bit CPU in each of our DRAM chip. So our DRAM chips is a 4 gigabit DRAM chip. So we have 8 banks of 64 megabytes. The CPU can run at 450 megahertz. On each CPU or DPU, that's how we call them, see only its bank, while the server processor will be able to see the totality of the memory, okay? And we put 16 of this chip on a DIMM. On the configuration our customer work with, typically they have 20 UPMEM DIMMs and 4 regular DIMMs. That's so for the second generation, we will do the things slightly differently. We will have twice the amounts of banks. The bank will be half the size, and we will have the same number of DPU. They will run faster, 600 megahertz, and they will have security features which are not present currently on the first generation. Our processor is a multi-threaded CPU. We have 24 threads in the current generation, and we will reduce this to 16 threads because of the feedback of client and the feedback of the application programmers. So at the thread level, instruction execution is done in order, but according to various hardware events, the threads can go before. I mean, the scheduling is flexible between the threads. When a thread requests execute a DMA instruction, typically it will reorder the thread execution significantly. And you see there is so this is not a picture of the chip; it's a picture of a DPU cluster. I mean, you are seeing 4 DPUs on their work memory, and oh, no. Sorry, that's a picture of the chip. Sorry. I was looking for a memory on my phone. No. Sorry. So you see I don't see if you see my mouse. Okay, so that's a processor. That's its work memory, work RAM, the instruction RAM. And you see you have 4, that's a cluster, north cluster, south cluster. And you have the DRAM bank on what is called the spine, which is the part where you have the I/O of the chip. Okay, so our processor have a proprietary Izzat. You can target an open source compiler. Thanks LLVM. Thanks a lot. That's a very convenient. It would have been very difficult to achieve 100% compatibility with anything. On 90% compatibility, that's not that much interesting. So we are on our own instruction set. Instruction set typically they are conceived with the goal of being efficient from the very simple MCU to the very big server CPU. And because of the DRAM process limitation, we know that the design envelope for PIM is far smaller because we know we won't be able to build a server CPU class inside the DRAM. This is not realistic. So when you know better the kind of implementation you will use, typically in order, and I will say scalar in order, then you can make choices which will otherwise be dangerous for an architecture which want to encompass a large design space. So it was very reasonable to have a proprietary Izzat. So we are doing on die processing. We use standard cells. We have to develop them because you have no offering like for TSMC. Okay, you have no SRAM generators, no standard cells. In fact, you have nothing. When you use DRAM foundry, you are on your own. So we use IP from a DRAM partner, which provides us with the DRAM, the DRAM memory array, which makes some arrangement for us such that we can connect our logic. On each processor, okay, see one bank only. The banks are really unaltered. I mean, we just ask the DRAM partner to add a mux such that we can either choose to have the regular path or to have the DPU which take over the DRAM array. That's that simple. We use a mainstream protocol, DDR4. So fundamentally, we can say that, for example, Samsung did the same approach as us, just they swapped DDR4 for HBM2. Maybe because we have a lot of patents on PIM on DDR4. No, but that's, no, we have very strong patent on this. I don't know why they choose this. So key things, and I will come back to this point, is that if you want to do PIM on DRAM, you have to start with the idea that you won't mess with the array. This is very complex technology. You have people specialized in this, and typically, it is not reasonable to expect that you will be able to modify the array. This is not a reasonable assumption. You will be able to ask the people doing the DRAM array and the stuff around it to provide you a connection. That's exactly what we request. But to modify the array, it's a kind of worm you don't want to open. Sorry. Okay, so the key properties of our systems is that since the DPUs in only their memory bank, the one they are associated with, our architecture is scalable ad nauseam. I mean that as long as you can add DIMM to your system, then you can add DPUs to your system. Because we don't have to provide a communication mean between the DPU. The memory protocols, therefore, in this occurrence, is what glue everything together. So you will be limited by the memory protocol and not by us, by our technology. Another aspect is that to establish inter-DPU communication will be very difficult things, extremely complex, likely more complex than the DPUs themselves. And the only company I know of which tried this approach failed. I'm thinking to, sorry, I don't remember how they were named. A company tried this something like 10 years ago. no avail. So we are use LLVM Clang based SDK. The processor is C on Rust programmable. You can even program it in assembly if you want, because instruction set, the documentation is open. There is no OS running on the DPU. There is no hardware to support an OS running in the DPU. But we have a software debug support. We have a few hardware extensions whose purpose is only to allow a debugger to provide a reasonable debugging level, a classical one. Concerning the current application, so genomics, analytics, search in database, and database as a whole. Obviously, AI is that's a hot topic. Okay, one problem with AI is that you need multipliers, and to have big multipliers on the DRAM, that's not such. Sorry?
Sorry, what is the protocol? I'm sorry, I'm a little late. Like, when can we ask the questions?
Oh, sorry, absolutely. I should have mentioned that it is better to ask questions along the presentation than later on. So please go ahead.
Yeah, I think that's a typo. You meant not Intel architecture, AI, right? New targeted application, right?
Sorry?
Yeah, that's AI. So new targeted application is AI. IA is a typo, yes.
Okay, okay, got it. Thank you. Thank you.
Yeah.
Yes.
You can also write questions in the chat at the same time if you think it's not necessary to be discussed at that point, then we can get back to it at the end of the presentation. So both goes well.
Sorry, AI, obviously. The bigger it is, the less you see it. On security, our next generation processor will have a very strong security because we don't have any OS running on the DPU, and DPU do not communicate with others DPU. So in fact, it is very simple, very straightforward to turn a DPU into a secure enclave. So this is exactly the feature we will add on the next generation DPU. And the key point is that since the DPU will not share any hardware resource between a secure application and application which will not be secure and potentially attacker, since there is no hardware sharing at all physically, then there is no side channel leak possible. And so that's a very strong property, because we have so many DPU in a system that you don't want to time share a DPU. You may have applications which use DPUs at different times of the day, but when an application is done using a DPU, then it will clean it and release it to the UPMEM driver such that another application can use it. But you see, it's not at it's an application level, it's not time sharing through scheduling. So this will make a very strong security due to its simplicity. So this is definitively a market we're after. Concerning the genomics, for example, so if you do a CPU solution only, you are going for 20 hours of calculation. We are currently here, you see 39 minutes. You see the GPU are just slightly faster and just something like 10 times or 20 times more expensive. I don't remember the exact price, but that was the order of magnitude. On the next generation of the, and if we add more, oh, there must be a typo because I see the frequency is lower than this. Okay, so there is some typo in the slide. Sorry for that. Okay, so fundamentally, we will provide. We will be on par. We are already on par with a very big GPU costing far more than our technology, burning far more power, and we do intend to gain speed advantage behind the economic advantage. We are very conscious that they are not standing still, and neither are we. So that's for the genomic pipeline. Sorry, because this is very painful to move the slides. It goes too fast all the time. Up, up, up. Okay, so that's a slide about the cost. On one interesting thing, genomics is a very good candidate for PIM because you can do a lot of most of the calculation using windowing. I mean that you will compare fragment of data with fragment of data, and then you will move this fragment and try to find where it fits. So this is very friendly to such that it can be subdivided in tiles. So really, genomics is really a very good application field for PIM because you don't need to have most of your calculation. There is really a lot of locality, and that's very good for PIM. That I will say essentially the basic argument for PIM is this one. So genomic is really a very good application. Okay, so you see, so on the TCO side, the argument for PIM is more obvious, is stronger than even for speed. And for speed, we intend to go significantly faster in the coming years. But you see, concerning the price, we are really there is a very big gap already. Okay, so you see that when we run a genomic PIM application, so we use a two-socket 86, two sockets such that we have the large number of DIM slot available. So we don't use all the memory, 90% of it, okay. You see that the instruction efficiency of the DPU is very good. We are almost executing one instruction every cycle consistently. From my point of view, this is a very good figure. The DPU are occupied 72% in average. Okay, sometimes the DPU has nothing to do because the way the calculations are scheduled. You request the DPU to check something, and then you will wait for those DPUs. So some of the DPU will finish early, so they will wait, okay? Because the way the application is scheduled makes this kind of scheduling all. We all the time try to improve these figures on all the applications we have, because that's something you observe on all the applications. And you see the PIM bandwidth is used, but not dramatically. What in this application, what we provide fundamentally is a lot of instruction and execution speedup. Is the fact that we have 2,000 processors capable of every cycle executing one instruction. So we have a system where you are executing 2,000 instructions every cycle. That's fundamentally the speedup we provide. Because we have the bandwidth, which is far than good enough, such that the bandwidth is not a problem at all on this application. And you see that this, when using this technology, the host processor still remain free almost 80% of the time. We need a dual socket just for the slot. In terms of calculation done by the 86, then your 86 is free to do a lot of other things. So there is other things than genomics, for example, index search, which is finding 5 words in a large database, a search that you can do auto-completion, things like this. And we have a very good results on this kind of application. We have a higher throughput, far higher throughput, far lower energy. There is one thing which is not shown in this slide is the latency. We provide the right transfer in something like 100 almost of the time the 86 does. Because 86 will use several threads to handle several requests at once, like us. But so the difference in latency and bandwidth is you see that we provide 10 times more bandwidth, but we have 100 of the latency. This is due to the fact that the 86 itself use multi-threading, multi-core, and so on to provide the bandwidth, but its latency is really long. And for application where the latency is critical, PIM really, it's for this kind of algorithms, you can win again doing the search in 2000 system in parallel. And that's what we are doing. So the latency is very good. And we are working on other very promising application. So PIM is worth it, definitively. And we are working with partners on all these applications. Too many to you read them. Because otherwise I won't have any voice left. So if it is so interesting to do PIM in DRAM, why was it not done before? And especially
excuse me, sir. Ishwar here. So I have I typed a couple of questions. I think before you move to the next section, it would be great if you can. These are related to the section which you have already covered. So in the chat window, I have specifically mentioned 3 questions. It would be great if you can answer those. Thank you.
Maybe you can, Ishwar, maybe you can ask them now one by one, now that you're.
Yeah, sure. I can do if he's that window is not there. So the first question is that I don't know whether you are aware there is a DLRM recommendation models, sir. So I didn't catch your name. I'm sorry. The presenter.
Fabrice.
Fabrice Devaux. Fabrice Devaux.
Okay. Yeah, so the DLRM is a recommendation model, and mostly I think this name is from Facebook's recommendation model. So have you used your product for in that, or used in that workload or not?
Okay. Fundamentally, we are an NDA with many big companies you can easily think of, and so I can confirm or deny that we are working with search company. I can tell you that we are working with some of the biggest companies in the world, clearly. That's what I can tell you.
Okay, no, I'm not interested in Facebook in particular. I'm generally particular in understanding whether you're working, your product can work on DLRM kind of models or not.
I mean, our product is really a classically programmable on steroid microcontroller with 64 megabytes of DRAM. So I don't know which application is not suitable for it, okay, you must have the most linear sequential application to have such that it is not interesting. But in fact, maybe you can port, there are algorithms you couldn't port on such an architecture. But if you see at the application level, you will see that you can reformulate the algorithms or use another algorithm and fundamentally solve the same problem differently. And I will say that the things we see the most is that if you see exactly the algorithm at the starting point, then you see that's not such a good candidate for PIM. And then if you go one step higher and you reorganize the calculation, you will see that there are many calculations that are amenable to PIM. So
okay, I think I'm not sure what
yeah, I
answered,
think
but we can go forward. Maybe the next question was yeah,
sorry,
somebody was saying, yeah.
Sorry. For the sake of time, I think since these questions are more like the discussion, and we have a discussion part after the talk, so
sure,
if
we can
you don't mind,
yeah.
we move that
Yes.
so that we make sure that we get the presentation in the next 10-20 minutes
sure,
done.
Sure.
So
Sure.
Thank you.
okay, so concerning, okay, so if PIM is that interesting, while wasn't it done before? Because that's very difficult. It's very difficult because DRAM processes are really bad to implement logic. The transistors, they are very slow. The routing density you have is something like 130 to 120 of the wires you would have on a similar process on the TSMC process. You have no IP, no standard cell, no SRAM generators, and no calibrated and established design flow. You are really on your own. I will say this is certainly a very big deterrent for startups, not necessarily for the DRAM players themselves, but at least you see the startups, it's very difficult to solve all this, to deal with all these problems. On the two first, everyone, the DRAM manufacturers, they have the same problem. I mean, okay, they can create their IP. So you see that it's brand new. I mean that we are the first company doing actual commercial PIM. So I can tell you, you are in the jungle with a machete, and you are progressing through the jungle. Okay, there is no road. On beside, on the ASIC side with TSMC, you have an highway, and that I will say that's fundamentally that's the difference. Another thing is that we wanted to be on the regular memory bus because of the existing infrastructure, obviously. And DDR4 is absolutely not intended to support PIM. In fact, everything in the protocol is against PIM. So you have the BIOS adaptation to do, no cache coherency. There is one very important point which is missing, is that you have to scramble the data such that your data from 64 bits this way, you have to push them into column to send them to the chip. And that's one of the patents we have. The cherry on the cake is that big server chip, sometimes they do things they are not intended to do, like writing something which has never been written, but only read, so they write it back. There is no reason why they do this, but they do this anyway. So, and you have a problem of power management because you will add so many processors in the system that you are adding a lot of wattage, a lot of power to the memory system, and you have to take care of this. Okay, so on a DRAM, fundamentally, you cannot do in-array calculation. The reason is very simple. It will mean you will share the electrical charge between cells. So this means that the result of this sharing, of this summation will have still a good noise margin. But the idea of the MRAM process is that they make the smallest cells they are able to read. And they are able to read, I mean that something like it's less than 5%. In fact, we are in a very few percent of swing that they amplify. So if you share the charge, you will just have something which is not readable anymore. So fundamentally, you cannot do this kind of things on a DRAM. You can do it on a non-volatile memory because it is not volatile. The small swing you will do at the end, it will stable, it will last in the time. While on the DRAM, you won't be able to read it. And even if you take 1 day to read it, you won't succeed in reading it and it will be lost anyway. So it is fundamentally, it is impossible. I know there are nice ideas about making a majority vote using charge sharing and things like this. Seriously, this is absolutely impossible to do on actual DRAM process. The ideas are interesting, but really this is absolutely impossible. Maybe if we have a time machine, we go back 20 years ago on DRAM process, maybe the few things like this will be possible, but nobody wants to go back to very low density DRAM. One other thing is that anyway, even if it was feasible, nobody will fab you, but just nobody. The DRAM people are conservative. They are running very expensive fab, several billion of dollars the fab, okay? If you are fab by a DRAM foundry, it's a favor. I mean, they believe your technology will work. They won't let you, even if you throw money at them, they won't let you play with, they don't want this. You see that I mean, at TSMC, I believe that if you are in a shuttle, they don't care if the design you are putting in the shuttle will work. They don't care. You are built and you pay the money and okay. On a DRAM foundry, that doesn't work this way. So even if it was feasible, and seriously, I'm very categorical about it, it's not feasible. They won't let you do it. They are not interested in this. They are very clear about this. And maybe that's the opening for the discussion. So some thoughts I had preparing this presentation is concerning PIM. Today, for me, there is two possibility today is DRAM and flash. There are other non-volatile memory technology, but the problem is the following: is that other non-volatile memory, they have been they have said for we will be ready, we will have something which works in 6 months, but it's just 20 years. Then they say in 6 months it will work. And I believe there is only one company which makes actual product, it's Everspin, which make magnetic MRAM memories. So, but the density is low, the cost is high. So technically, it's possible to do this, but I don't think it's economically realistic. And I will say for the other non-volatile memory, you have to wait until they really work. Then maybe we can think of doing PIM on this memory. But to try to make PIM on a technology which is not proven, really, that's a losing proposition. It's too much risk by too much risk. It just okay, so that was a reflection about all the non-volatile new memory poised to succeed in 3 months all the time. One other thing to consider is what kind of product you want to do. I mean, you can either want to do a memory which has processing capability, that's UPMEM vision. Or you may want to say, okay, my product is not that much a memory. It is a memory in the sense that it's the way I will do the calculation. But it is primarily an accelerator on which use memory as a mean of calculation, or which is based around the memory technology. So you see your price, your density, your price, your power, objective vary completely if you want to be one or the other. I believe there are markets for both. We are pursuing more a memory-centric approach, which is we try to make memory clever without dramatically affecting the manufacturing cost of the memory. I do believe for AI or other applications, specialized application, you can build an accelerator based on a PIM technology. On other things is effectively concerning the stacking, really the problem of removing the heat when you stack is really a big problem for PIM when you want to stack PIM DRAM or PIM whatever, and when you want to sandwich logic die with memory dies. The thermal aspect is really a problem. And if you want to work with PIM, you're welcome. You can use our SDK. There is many examples. We have a data center. You can run hours of calculation, and don't hesitate. It's a reality. PIM is there. And that's it.